Hello, good morning, and thank you for being here. Thank you for being here early in the morning for the last day of the conference. So I have to thank you twice with all the activities that you had on the other night to be here early in the morning. My name is Sebastien. I'm part of the developer relationship group, the developer advocate group of Amazon Web Services, and I'm always a bit excited to talk at Devoxx because I'm attending Devoxx since forever, since even before the name Devoxx existed. It was Javapolis at the time, talking about early century. For those of you that didn't know that Devoxx had another name before, and also because I was born and raised in Brussels, not far away from here, so I feel like I'm talking at home, which is not frequently. I will not talk too much about AWS today. It's more about architecture. Of course, I will illustrate that with AWS services because I have an AWS logo on my shirt, and that's what I know and what I can talk about. But today we are going about how you embrace failure, how you test software, and what type of design patterns can you use in your software architecture to be more resilient. Just a quick poll first before starting. How many of you are running IT system into production? I guess most of you, otherwise you wouldn't be here. Who had a failure already? Don't cheat. I know you did. If you didn't raise your hand, now come to talk to me at the end because I'd like to know how you're doing that. And just for my own curiosity, how many of you are running production systems in the AWS clouds? Roughly half of the room. Perfect. You know that traditionally we are testing systems in isolation, like unit tests, some integration tests, and then we deploy to the cloud or we deploy to our data centers. And actually today distributed systems are a bit different. It's difficult to test all the possible combination, and you always have that specific request that is arriving into your system and behave a bit differently than what you expect. So you might have planned for everything. You have a belt, you have suspenders, you have safeguards, you have alarms, and then you have that user that behaves in a way that you didn't really expect and cause some kind of catastrophic cascading failure that you really did not plan for with consequences far away from the problem directly. And the best part of that video is now. So, distributed systems are hard. They fail all the time. And if there is one thing that you can be sure about your distributed system, is that they will fail. It's not a question about when or how. It will fail. And the best way to manage that is to embrace failure and build systems that are resilient over time. So resiliency for a system is the ability to continue to operate, maybe to operate in a degraded mode, and we are going to talk about that, but to continue to operate and maybe even recover from unexpected condition. Very good example of system resiliency is this one. Continue to operate in partial failure mode. That's exactly what you need to do with your software. And actually, it's possible. And I'll show you a couple of techniques that you can use to continue to operate. So resiliency, it's a matter of 4 different things. It's, of course, the infrastructure. The infrastructure itself has to be resilient. The network and the data, you need to replicate the data. You need to have backups. Yes, I'm going to talk a tiny bit about backups today. But your application needs to be designed for resiliency as well. And there are a lot of things you can do as a software developer to ease the pain in case of failure or to recover from failure. And then there is the process and the people. And that's the part I will not address too much today, but I can probably have a full talk, one hour talk about processes and people inside the resiliency pattern. I call that the pull factor. Or yesterday, during the keynote, we call that the truck factor. Remember the keynote yesterday? The Paul factor is because I work in a company where we had that guy named Paul, and that guy was able to fix any problem into production. You know, that's the type of guy that's fixing live production issue in production and developing a new feature at the same time and calling his mom on the third line. You probably have a Paul in your company, don't you? Yeah. And what about your business is when Paul is not there, when the pager is down or is off the network? So that's the people factor. I will not address that. I will focus today on infrastructure, network and data, and application. So the first thing you can do to build resilience into your system is to be redundant. That's something we are doing all since quite a lot of time. You don't have one server, you have two servers. You don't have one load balancer, you have two load balancers. You don't have one coffee machine, you have two coffee machines, and so on. But obviously, putting all your load balancer, all your server in the same rack, in the same data center does not help a lot. Yes, it helps to prevent some failure at the server level, but what if your data center is out of power? Or what if a plane is crashing on your data center? You don't have resilience. So you need some kind of geographic distribution of your server as well. And at AWS, we have 22 different regions where you can deploy your application and your data. And we've announced 4 new regions, mainly in Europe, Milano and Madrid, Cape Town and Jakarta. So the first thing is you do not need to put all your eggs in the same basket. You can actually deploy your application with a server in London, another one in Frankfurt, a third one in Paris, for example. And having that kind of geographic distribution helps a lot. Mining, and I know that it introduces other complexities, like the latency to replicate the data, maybe some legal complexity. What type of data can you move outside of Europe, for example? But inside a region, we have that concept of availability zone. And availability zone is one of the basic building blocks to build highly available application. So an availability zone, it's a group of data center. It's not one data center. It's a group of data center that are isolated from each other in terms of failure. So when we build a data center, we list all the possible failure. It might be network is down, power is down, it might be a flooding, it might be an earthquake. And we build this availability zone in such a way that if one event affects one availability zone, the other will not be affected by the same event at the same time. In San Francisco, it means that we are putting our data center on different sides of the big reef. So when there will be a big earthquake in San Francisco, we might lose an availability zone, but we are not going to lose 2 availability zones because of the same reason. So what we are doing with availability zone is basically to expose our limit of failure or failure protection zone. And we document that so that you can take advantage of that for your application. So basically, we are showing you the basket where you can put your eggs. And don't put all your eggs in the same basket, because we are telling you, yes, an availability zone might fail, but we designed the system to avoid the other availability zone to fail at the same time. So redundancy, and through the magic of math, helps to improve availability. If you have a system which is available 99% of the time, means a downtime of 3 days per year, roughly. Just having 2 systems in parallel, if they are independent, you reduce your downtime to 50 minutes per year, and 3 systems, 31 seconds, and so on. So typical cloud architecture, maybe you saw this type of architecture before. You have web server, you put 3 instances of your web server in 3 different availability zones, and you put a load balancer in front of that. If something goes bad in one availability zone, might be your server, might be our problems, the load balancer will detect that and will stop sending live traffic to that server. Same for the database. If you have a master-slave database, we will detect automatically that the master is down and will promote the slave as a new master. So eventually, all the traffic will shift to the remaining availability zone, 2 and 3 in this example, and your system will continue to operate, even in the case where a catastrophic failure happens inside your application or inside the availability zone. So that's really the basic stuff, and I wanted to start with that because that's the most basic things you can do to enable fault-tolerant application. Don't deploy your application in one single data center, always spread across multiple data center. And if you're using the cloud, try to use regional services such as Amazon S3 or the load balancer that are designed to work with these availability zones. I mean, Amazon S3 knows that there is multiple availability zones, so you do not need to tell, I will put my file in that availability zone. No, Amazon S3 duplicate your file, replicate your files automatically across availability zones, and should not fail in case of one availability zone failure. So in all our regions, or new regions, we have 3 availability zones that you can use from. What about auto-scaling? That's, auto-scaling in public cloud is this service that allows you to increase your patterns, increase the number of servers you have depending on the load. If you have high load, you increase the number of servers. If you have low load, you decrease the number of servers. Auto-scaling is a very good service. I used to call it as the poor man cluster, because auto-scaling will also respawn failed instance. So if you have a virtual machine that fails for whatever reason, auto-scaling will detect that and will automatically replace that instance. So for small application that can afford to have a few minutes downtime, or of development server, or things like that, auto-scaling, it's a very easy way to get an automatic restart of your infrastructure, of your machine. So if you have an auto-scaling group with minimum quantity of 1, if one instance fails for whatever reason, auto-scaling will automatically recreate the instance and re-register the new instance with your load balancer. I recorded a very short video demo of that in the AWS console. On the right side, you see one instance, part of an auto-scaling group, and I terminate that instance. So it warns me, hey, terminate is kind of definitive state. You cannot resurrect an instance. And auto-scaling is to configure here to have one instance up and running all the time. So it will detect that my instance is down. It will, if I refresh there, it will detect first it's an LC. And then in the history, refreshing the history, we see that it detects the unLC one. It's launching a new one. You might have to wait a bit if you have scaling policies that says, hey, wait between different events to ensure that the system stabilizes before creating a different instance. But eventually, if you refresh the EC2 console, you will see that a new instance has been created. So that's poor man's cluster, a very easy way, cost-effective way to replace your instance. Something else about backups. I don't want to bore you in the morning, but I guess you're doing backups. Do you? Yep, most of you. Backups, it's not so much to prevent a cloud failure. We replicate a lot of data, but it's more to prevent human failure. You're doing just that last administrative task, and then the system is down. The command line there, it's something I did on a production server on a Monday morning. We had a warning during the weekend that this space was going to be full. Okay, so I checked the log directory, I transferred the log to a shared file server, and then I was ready to delete the log directory. And there is tiny space between the slash and the var. I don't know if you can notice that, which makes the systems not exactly behave like the way I expect. And that command did not return quick enough. So I say, hey, what I'm doing? And then, one of my colleagues in my team did almost the same, but it was in an Oracle database. Drop database, drop table, and oops, it was on the production database and not on a test or development database. So when you do that, you have two options. You have to search. Either you search for your backups, either you search for a new job. You really have to have a backup. So we have a service that can help you with that. You can also, and that's one of the nice things with public cloud, put multi-factor authentication on some sensitive API, like an API to delete a table. You can protect that, asking the operator to enter a one-time password. So it allows the operator to think a bit more. Instead of just typing enter, you need to find a token and enter the token. It gives you a few extra seconds to think about what you're doing and maybe to not type enter if you are not in the correct environment. So don't forget about the Schrödinger state of backups. As long as you are not testing backups, they are not really existing. They are in an intermediate state. Test your backup. That's the difference between a system engineer and a good system engineer. The system engineers are making backups. Good system engineers are testing the recovery. That's for the infrastructure. Now let's see what you can do at the application level. And one of the patterns we observe more and more with our customer, and certainly one of the patterns that we adopt at Amazon since a long time, since we operate a very large system at scale, we learn different patterns. I'm going to share these patterns with you for the rest half an hour. One of the patterns is work asynchronously and decoupling calls between different components. Amazon S3 or Amazon DynamoDB are very good systems that works asynchronously. Everything happens with asynchronous calls behind the scene, and this system can scale to very large number. Amazon S3 regularly peaks at millions of transactions per second. During the last Prime Day, you know, the big shopping 2 days promotion sales on Amazon.com, DynamoDB peaked at 44 million transactions per second. So this system can scale to something beyond my mind, 44 million transactions per second. And one of the reason is the asynchronous nature of this system. So you all know that if you call a web service or another dependent system, your client code can wait for the call to return, or you just drop something and wait for the result to come asynchronously, and you can continue to work behind the scene. A great way to implement asynchronicity is to use queues. You have the client calling your API layer. The API just put a message in the queue with a job ID and immediately return to the client. And then you have a fleet of workers in the backend that will pick up this message from the queues and process the message at their own rhythm. It allows to protect the API in case the worker is not working anymore, or if the worker are slowing down. The API can continue to respond to your client calls quite efficiently. When the worker is done, it put the result somewhere in memory cache, database, whatever, and then you can use notification systems to actually inform the client that the data are there. So you push a notification, and the client can make another API call to fetch the data from the call. It allows also to scale these two layers at their own pace. So maybe you do not need the same instance type, you do not need the same hardware characteristic just to serve your API and your worker, so you can scale and you can optimize also for price. Another good thing with queues is that you can use queues to prioritize traffic. So instead of having one queue, you can have two queues, like low priority, maybe for a free customer, high priority for paying customer, or for API calls that are more sensitive for your business, that are more critical for your operation. And you give different fleet size, different priority for the worker picking up the message on the high priority queue versus the low priority queue. It also helps in case of degradation. If your system is working in degraded mode, you can configure a system to only handle the traffic on the high priority queue and not on the low priority queue. That work can be left for later when your system will be back to life. Scaling database and being resilient with database, that's one of my favorite interview questions when I'm interviewing for technical roles at Amazon, is give me your option to scale your relational database. And actually there is not so many options to scale a database. You can scale vertically, but at some point you will hit the maximum number of memory and the maximum number of CPU you can get from your platform. So one thing that we learn at Amazon, and we are playing quite a lot, is to decouple the read and the write operation, and especially when your application is in degraded mode. When you're in degraded mode, maybe you can continue to serve your customer, but only in read-only, and queue the request for write while waiting for your database to recover. Anyone implemented that already? Read-only mode? 1, 2, 3, 4, 5. I can count you on my finger here. Another way to scale database is divide and conquer. Instead of having one giant relational database, it's split database. We call that database federation. For example, you have your product database on one side, your user database in the other side. It allows to scale your database differently depending on the API calls on these database, or even to implement database sharding. And when we are using a lot of relational database, we do implement that quite a lot. You have to find a shard key, might be a hash of the username, for example, and say, okay, all user with that type of username will go to the first DB instance, all the others to the second DB instance. It allows to scale really well and quite horizontally your database load. One of the disadvantages, of course, if you have to make a lot of relational calls like joins, select from between multiple tables, it becomes quite difficult to manage relationships between tables. My favorite is about timeout, backoff, exponential backoff, and retries. That's a design pattern we are also implementing quite at large scale at Amazon.com. Basically, there are two types of failure. There is a catastrophic failure, the one that happens immediately. You have no more power, no more network, your server is off, and these ones are quite easy to catch because it's obvious, it's there in front of you. And then there is these little errors that happens once in a while when your network is getting slower, when you have a I/O constraint, when you have a couple of packet loss or something like that. And one good way to transform these transient error or errors that are difficult to detect into catastrophic error is to use timeout. Okay, I'm stopped waiting for you, just let's raise an exception and I will let the rest of the world know that you are not behaving correctly. You are too slow for me right now. So timeouts, very effective ways to manage that. But timeout can be a bit evil. Imagine that you have a client application talking to an application server. That application server is making a lot of calls to a DynamoDB or any type of relational database. And your database is slowing down progressively. So what will happen in that case? And of course, you have timeout on the application server side. You also have a timeout on the client side. But when it's the last time you check the value of this timeout? Anyone check regularly the value of your timeouts? Anyone ensure that the timeout on the client side is actually larger than the timeout on the client side? Never use a small timeout towards a large timeout. Do the opposite. What happened? I'm a client application. I'm calling an API on the app server, and the app server tried to call the database, and the database is slow. So eventually the app server will catch a timeout, or maybe not, if you have a larger timeout on the client side than a smaller timeout, sorry, on the client side than on the app server. Your client timeout will kick in before the server timeout. So it's the client that will timeout. And of course, you are a good citizen, you're a good software developer engineer, so you learn that when something fails, you need to retry. So you retry, but the database is still slow, and so on, and so on, and so on. So you will use a second DB connection that will never return, and the timeout will kick out again on the client side. So, of course, your application retry. And if you have hundreds of applications doing that, hundreds of clients at the same time doing that to your application server, you're basically creating a DDoS attack to yourself there, because at some point, you will get that threaded exception. You exhaust all the connection from the connection pool. And it might be on the application server side, might be on the database side. You have reached maximum number of connection. So what can you do? First, examine and study the timeout. Whatever programming language you are using, whatever database you are using, be sure to check the documentation. How do I set the timeout on my database in my app server? There is timeout for all types of systems. I don't know any systems like that without a timeout. My preferred is this one. Because look at that, timeout in milliseconds on network socket operation. Default is 0, and 0 means no timeout. So if you're using MySQL, beware of that, and be sure to use a specific value, because by default, your ConnectG driver will not timeout. You can also add timeout at your code level, and there are tons of libraries to help you to do that. You do not need to code low-level threading stuff. The timeout decorator in Python, for example, is a very good example to generate timeout, even if the underlying call is not managing the timeout properly. So seriously, guys, put timeout, define timeout in your code. So what could you do to prevent the timeouts there and to prevent, to exhaust the connection pool? One thing we do at Amazon, we are using exponential backoff. So instead of retrying automatically and generating a flood of requests on an app server, we write code in such a way that we are going to wait a bit during the retry. And that wait is exponential, like I will wait 2 seconds, and then I will wait 4 seconds, then I will wait 8 seconds. So providing that you have set the timeout correctly on the application server side, your retry logic will eventually happen at 16 seconds there when the application server starts to release connection and make connection available again for your application. It will release connection, and your client will eventually retry. So we did that for a couple of years at Amazon. It was working quite well. But we realized one pattern which is still causing problem at large scale, is that if you implement the same exponential back-off logic across all your clients, imagine a problem happens, and all your clients start the implementation logic roughly at the same time. So all the clients will try to reconnect to the application server roughly at the same time as well. And this is what you can see from the left graph. You have all these retries, so it's the call count versus time, and you have all the retries that are at exponential back-off time. So what we do to flatten that graph, we introduce a jitter. A jitter, it's a complex name for a bit of randomness. We take a dice and we choose a random number to add to the exponential backoff. And that way, if each client uses a bit of randomness in their code, you can flatten that graph and have the graph on the right side that shows you that the calls are spread over time. So especially in difficult time, especially when your DB is under degraded mode because of too many calls, it's important to not cause additional pressure on your scales resource at that time and to flatten that course. So how do you add randomness? It's one line of code. Instead of just waiting to exponent the number of time, you add a bit of random. In this example, it's between 0 and 1 second. So whenever you're making network requests, database, web service, microservice, whatever you call them, be sure to have that kind of retry mechanism. It's quite easy to implement, exception. Be sure to get out of your loop as well. So be sure to have something like this. Otherwise, you will retry forever. When we apply jitter, we can see that the number of calls per number of competing clients is actually decreasing. So the top graph on the top line on that graph is when there is no exponential backoff at all. And when we add exponential backoff, it's the green line, the second one. And when we add jitter, it's the two lines from the bottom that are almost not distinguishable there. That's the number of calls we observe on some system when we implement full jitter. So one line of call, one line of code can lower the pressure on your resource. If you are retrying, think about that as well. Idempotent, I'm unable to pronounce that in English, sorry guys. Idempotent operation. So whenever you make a call with the same parameter, it has always to return with the same value. It's much easier to say right here in a conference than to implement in real life, but that's probably a subject for another one-hour conference, how to implement idempotent operation on your database. One way to manage with timeouts as well is to use circuit breaker. The idea of a circuit breaker is to have like a proxy between you and your service. So instead of calling the service directly, the API or the database, you call the proxy. And the proxy will make a health checks on the system, and it will avoid calling the resource if the resource is not available. So it will immediately return to your call without putting additional pressure on your resource. There are many different libraries that help you to implement a circuit breaker inside your application. You can implement your own. This one is a bit old. I know it's not fully maintained anymore by Netflix. It's historics, but it's a very good example how it can be implemented. If you look at the code, you have a call making an API call here, reading list, which is an API to an HTTP API. And this call is protected with an annotation that says, in case of a timeout or in case this is not working, maybe the backend system is not responding, then fall back to this method, reliable. And reliable is there. And here in this example, we just return a hard-coded value instead of a value from the database. And that's another design pattern that we applied quite at scale, is to return default value. If your system, if your database is down for a period of time or is slowed down, just return something. It might be from a cache, it might be from your CDN, it might be hard-coded value, but at least the client making the call will receive some data. I will have an example about Netflix doing that as well. Health checks. a lot of developers are not paying attention enough about health checks. In a typical cloud architecture, health check is something made by the load balancer. The load balancer will call a URL that you define on your application at regular interval of time. And as long as your application responds HTTP 200, okay, then the load balancer knows that the application nodes are okay, and it will continue to send live traffic for these nodes. If the health checks times out, or if you return anything else than HTTP 200, like 500 or 400, then the load balancer knows that that node is not working correctly, and it will remove the node from the load balancing game. It will eventually replace that node a bit later if you are using auto-scaling. So health checks are quite important, because if you misconfigure the health checks, or if you are not replying to the health checks probe sent by the load balancer, it means the load balancer will eliminate, will isolate that instance from your infrastructure. And when you're in time of scarcity, of trouble in the system, you don't want that to happen. If the node is valid, it's up to you to correctly answer the health check probe. So there are two different types of health checks probe. The load balancer always calls your front-end instance, and either you can just return something from the front-end instance saying, okay, I'm there, without taking care of the back. But you can also implement a deep health check probe, because a shallow health check will not detect that a backend resource is actually failing. So deep health checks, it's actually the instance that are going to check all downstream systems, database, API, microservice, whatever, to ask them if they are healthy. If they are healthy, if everyone is healthy, then the front end will return, yes, I'm healthy and the system is working correctly. This is not new. This is something I did implement like more than 20 years ago with mainframes in a bank. The front-end mobile application that we were developing at that time, it was a website at that time, used health checks to check the downstream, including mainframe. So we were sending MQ message to a COBOL application, and we asked the COBOL developers to return. It was not JSON at the time, it was XML, to return an XML probe saying, yes, the DB2 database and the mainframe business logic is still healthy and can still work. Prioritize shallow health checks. If you have resource constraints, if you are in degraded mode, don't add more load to your system by ensuring that the system is still working. So shallow health check works for degraded mode. Be careful about logging also with your health checks, because if you log every single health checks, like let's say every 1 second, that generates a lot of logs files that you need to store and to filter and to search. So it might make your logging a bit more difficult. What about load shedding? Load shedding, it's something I try to do for my professional life as well. When my manager says, hey, Seb, you need to go to talk to DevOps, I say yes. And then Web Summit London, it was this week as well, yes. And reInvent AWS conference at Las Vegas, yes. But at some point, I will be overloaded, and I have to say no. I have to reject some of the load. And I guess it happens to you every day in your professional life as well. You can apply the exact same idea to your web server, to your API. If you know the amount of load that your baseline system can absorb, it's perfectly valid to reject some load that is over that threshold. So the first thing to do when you want to do load shedding is actually to measure your baseline, is to know where you are, know how much request you can absorb per minute or per second. And if you are approaching that baseline, start to just reject the work. And okay, it's a bit cheating there. It's, instead of taking your request, you just reject them. You return with an HTTP 500, and the client will retry with exponential backoff strategy, for example. There are many software that allows you to do that. The old load balancer in the physical data center, or firewall. I remember Max Connect type of properties that you can tune in. On AWS, if you are using the API gateway for REST, we have a throttling limit, and the throttling, it's exactly that. You say, okay, I will accept 100 transactions per second, but everything above that will be just rejected with an HTTP error, and you will have to, the client will have to retry. We don't support that in our load balancer yet, but okay, that's something which is frequently asked by customers as well. So rejecting, cheating, it allows you to take control of the outage instead of the outage taking control of you. It's a very effective way to do that. Don't be overly optimistic about the quantity of work that you can do. So try to measure what is your baseline, and that's probably the difficult part of load shedding, and to find the correct metrics. What will be the metric that will define when you need to start to reject some work? Is it CPU average on your fleet? Is it memory usage? Is it transaction per second? Is it? It depends really on your application. In case of shedding loads, try to not just reject with HTTP 500. That's the most basic and easy thing to do. But you can also just return pre-existing content. Instead of fetching personalized content for your customer, you return a hard-coded list, hard-coded value that will be shared against across all the customer. And please never reject your ping health checks, because if you start to reject these, you will actually trigger your load balancer, your auto-scaling or whatever to trash your instance, to replace them. And if you start to reject, it means you're already in trouble, so you don't want to add trouble to the trouble. Be scarce. Netflix is doing that quite well. You know, on the Netflix page, you have all these recommendations for you, for your country, and so on. And these are all different microservices that the client is calling to get this list. In case of overloading, they just return pre-cache content. It will be the same content for everyone, so it will not be personalization. It will be a hard-coded list of recommendations, maybe coming from their CDN, so that request will not even hit the backend. It will be just served from the CDN. And we are doing the same on the Amazon.com main webpage. We have more than 100 different microservices that are fetching the content to assemble that page. And if one service is not replying, or you will receive predefined hard-coded content instead of personalized content there. If you don't do that, a customer can see a page like that. And I'm very sorry for our friend at Reddit. I took that example. I could take another one. I love Reddit. But you have the client application calling different services, and these services are not returning anything useful. So you have a white, empty page in front of you. Last one I would like to talk about, last design pattern, is about shuffle sharding. So that's something we learned from operating large-scale system at Amazon since 20 years, is to avoid the blast radius. So let me explain that in a hopefully effective way. Let's imagine that you have a fleet of 8 servers, and that fleet of 8 servers serves, oops, I have a line that changed a bit, serves requests from many different customers. So I have my customer there. And then there is one customer that is sending a bogus request. Maybe it's different data set, maybe he's doing something different that you didn't really test, and it makes your application server crash. So poof, no more application server. And of course you are a good citizen, so you implemented back-off retry, so the client will detect that the call failed, and it will retry, and it will retry, and retry, and retry, and eventually all your fleet will be down, probably faster than you can realize what's happening there. So when this happens, all customers are affected, and that's the blast radius. It's the number of customers. Everybody is affected by that outage. So can you measure that, and can you try to minimize the blast radius? It might be the number of customers that are impacted. It might be the number of functionalities. Maybe it's not the whole application server which is done. It's just a couple of APIs or a couple of function calls. Maybe it might be a location. You define it. It depends really of your business, of your application. Let's continue with the example with the number of customers being impacted. And let's try to limit the number of customers impacted in case of such a failure. That's what we call isolation and sharding. And it's not a new concept. Actually, people building boats are doing that since many, many years. You isolate the different compartments of the boats. If there is a water coming inside the boat, this type of sharding will avoid the water to spread across the entire boat and sink the entire boat. So let's apply exactly the same concept to our infrastructure. So I still have 8 servers, but I create cells. Here my cells have 2 servers. server. And I use some kind of routing mechanism to send traffic from one specific customer to one specific cell. So it can be hard-coded inside your application, proxy front-end. We start doing that at Amazon. We were hard-coding based on the hash of the username and assigning cells hard-coded inside the code. You can have more dynamic techniques as well, like using a metadata repository to know which cell is assigned to which customer. But at the end, you assign your customer to specific cells. So in this case, I still have my bogus customer sending a bogus request that trash one server. And of course, he's retrying, so he's trashing that one. What is my blast radius here? It's only 2 customers that are affected. It's only the bogus one and the hurt. So the blast radius here is the number of customers divided by the number of cells. In this case, it's 8 customer and 4 cells. So how can we improve that and make that even better? And the idea would be to not assign the same customer to the same cells, spread customer requests across multiple cells, something like this. And we call that shuffle sharding. So now my customer will not be assigned to one single cell, but to 2 different cells. And I will do that randomly across all my customers. So this guy will be assigned to cell 1 and cell 2, this one to 3 and 4, and you got the idea. All my customers are randomly spread across multiple cells. So now what's going to happen there? If I have my bogus customer sending the bogus request, it will destroy one node in the first cell and one node in the second cell. But this guy can continue to use the application because there is still one node serving that cell. And this guy can still use the application because there is still one node serving that cell. So what is the blast radius here? Maybe you did a bit of combination when you were at school, remember? Shuffle cards and dice and stuff like that. So the blast radius here is the number of customers divided by the number of combination. And we love math. The number of combination can explode. So if you have 8 nodes and 2 shards, the number of impacted customers will be roughly half of your customer if you have no overlaps between customers and shards. If you have 1 overlap, it decreases. If you have 2 overlaps, it decreases to 3%. So at Amazon, we usually have 100 nodes in our fleets with a shard size of 5. And depending on the overlap that we do between customers and cells, it can go down to almost 0% of the customer impacted if one bogus request, if one unfortunate event happens inside your application server. So how do you implement shuffle sharding? You need a fault-tolerant client that will retry. And remember all the things we said about timeouts, exponential backoff, jitter, still apply there. And you need a routing mechanism. So you need like a proxy of front end that will assign a customer to a specific cell. At Amazon, we are just using DNS. You can have hundreds, thousands of sub-DNS domain. We have systems with millions of sub-DNS domain, and you just assign one DNS domain to one customer or a couple of customers, and that will be the cell for that customer. And it works with many different types of resources. You might have API server, database, queues. You can create cells and start to do customer sharding between different cells. Finally, let's talk a bit about chaos and the way to test that. We can probably talk about chaos and have a full conference dedicated to chaos and chaos engineering. At Amazon, we call that a game day, and it was created by this guy, Jess Robbins. I invite you, if you're interested by chaos engineering, to look at that video on YouTube, where the idea is to test the resiliency of your system through destruction. On purpose, you are injecting failure into your system to see how the system will behave and how the people will behave as well. So it's really a process of experimenting. You define a baseline. You have to know exactly the baseline of your system, how your system behaves, what are your different metrics under normal condition. You create an hypothesis. What if my database is answering a bit slower, like I have 1 second extra latency or 5 second extra latency in my database? What if? And then you inject the failure. There are different tools. I can talk briefly about the different tools. You inject the failure and you observe the reaction of the system. Do you monitor the difference? Do you catch an alarm? Do you have people that start to look at that after how many times? How long does it take before someone reacts? Maybe your client is super well designed and nothing happened. Good, that's the objective. But most of the time it's not the case, and something will fail. And how much time does it take to the team to detect the failure and to fix the failure? And then after that, what can you change in your code, inside your architecture, to be resilient to that type of failure? Okay, that's the idea of chaos engineering. There are a lot of tools. I like the open source Simian Army set of tools from Netflix that allows you to experiment at different level. It might be at architecture level, the instance, the network, but also at application level. What if your application start to return HTTP 400, 500 randomly? How the client resists to that? And so chaos engineering is really about experimenting, but experimenting in a controlled way. I'm not telling you to insert chaos into your production system. It has to be controlled. You have to have circuit breaker. Be sure to be able to stop the experiment if something goes really bad, because at the end you don't want to impact customer experience. So it's really about experimenting, measuring, and see how the systems are reacting and how the people are reacting as well. And it doesn't have to be catastrophic failure. With something like Simian Army from Netflix, you can simulate a whole AZ, availability zone, going down. That's quite a large impact, but it might be very small things. You can experiment with chaos by yourself. Just SSH to your server and use a tool like stress to increase the CPU load or increase the I/O or increase the memory usage, and see how your application will work when there is 90% CPU all the time, or when the I/O will be used by the stress tool. One thing that I like to do is just use IP tables. IP tables is very efficient. Just block the DNS traffic and see what will happen inside your application if there is no DNS resolver which is accessible. There are other tools like stress that allows to inject a bit of latency inside the network and observe how your application or your API is working under high network latency condition, which might happen. So it can be small things that you do at the host level. It can be big things like an attack on a specific availability zone or even a specific region. But the build is to gain confidence. You need to be confident that your application will continue to work, to operate, maybe in degraded mode, with read-only mode, but continue to operate and provide a good customer experience to your customer. So if you want to learn more about all that, we have a tool called Well Architect that has been developed by our solutions architect. Over the year, talking with customer, we established like a kind of white paper about what is a good architecture in the cloud. And it has 5 pillars: the operational excellence, the security, the reliability, the performance, and of course cost optimization as well. And we can analyze your architecture automatically to give you a checklist of things that you do already or the things that you might improve to be better in one of these 5 pillars. Most of the content of this talk, I copy that, or I get inspiration from my colleague Adrian Hornby. If you want to learn more about resilience, I strongly invite you to read his blog post, his multi-part blog post that explain in much more details all the design principle and the architecture pattern I talk about today. So patterns for resilience architecture. There is more than 4 parts. We continue to improve that blog, and we are pushing him to write a book on the subject. I really would love to have a book on that subject. So the idea is plan for the worst, because the worst will happen, and be prepared for the unexpected. Thank you very much. I will stay here and answer your question after your talk offline if you have any question. Thank you. Have a good day.